Hey everyone! Ever wonder why your insurance rates might feel unfair, even if the company never asks about your gender or race? Or why a loan algorithm could still favor certain groups without trying to? Today, we're diving into a breakthrough concept in AI fairness called marginal fairness, and why it's essential for building systems that treat everyone equitably, even when the math gets complicated. Let's start with the basics. Traditional fairness approaches focus on predictions, like ensuring a model doesn't wrongly label someone as high risk based on race. But here's the catch. Real-world decisions aren't just about predictions. Take car insurance. Companies don't just guess your risk. They set premiums using risk margins, capital charges, and financial rules. These are guesses, they're decisions shaped by math. And that's where fairness gets tricky. Most fairness frameworks ignore these risk-based components. It's like judging a cake's flavor by only tasting the sugar, missing the whole recipe. That's where marginal fairness comes in. It's a new way to ensure decisions stay fair, even when using risk measures. So what's the core idea? Imagine tweaking a recipe. If you swap a pinch of salt for a dash of pepper, the final dish should stay the same if the recipe is fair. Marginal fairness works similarly. It checks if small changes to protected attributes, like gender or race, in the data cause the algorithm's decision to shift unnaturally. If they don't, the system is marginally fair. Here's how it works. Researchers split decision-making into two steps. First, they build a model using all data, protected and non-protected, to predict outcomes like insurance claims. Then, in the second step, they apply a risk measure, a mathematical tool that accounts for extreme risks or financial buffers. But here's the twist. They tweak this risk measure to ignore protected attributes. It's like using a secret ingredient in the batter, but making sure it doesn't affect the final taste. Why does this matter? Let's say an insurance company uses gender in their internal risk model, allowed in some regions. But when setting premiums, they don't want gender to influence the price. Marginal fairness ensures that even if gender is part of the model, the final decision stays fair. This aligns with real-world rules, like the EU's gender-neutral pricing laws, which prohibit using gender to set premiums, even if it's used in internal calculations. But there's another layer, cascade sensitivity. This checks if biases might sneak through other variables. For example, if a model uses zip code as a proxy for race, the system should catch that. It's like a detective tracing how a hidden bias might influence the final decision. The researchers tested this framework on auto insurance data and found it outperformed older methods, like fairness through unawareness, just removing sensitive data, which often fails. By mathematically locking in fairness constraints, they built systems that are resilient to bias without sacrificing accuracy. Now let's break down the math. Think of sensitivity analysis as a fairness checkup for machines. Researchers use a tool called a generalized distributional transform, a math trick that adds randomness to data, helping untangle how protected attributes like gender or age might influence outcomes indirectly. For example, if a variable like credit score correlates with gender in the data, this method separates the real signal from the bias. They also test how small changes in protected attributes affect decisions. Imagine tweaking a person's gender in the data by a tiny bit, like flipping a coin to see what happens if they were slightly more or less likely to be in a certain group. Then they track how that ripple affects other factors, like income or credit history, and ultimately the decision itself. This is called sensitivity analysis. It's like asking, how much would this decision change if we adjusted a protected attribute just a little? The study also introduces cascade sensitivity, which looks at the whole chain of influences. For instance, if age affects job stability, which in turn affects creditworthiness, a bias in age could indirectly impact loan approvals. Cascade sensitivity maps these hidden pathways, so we can fix biases at their source, not just the symptoms. The real magic. They turn this into a formula for marginally fair outcomes. This isn't just about being not biased. It's about balancing multiple factors so no single trait, like race or gender, overshadows the real risks. For example, if a community has been historically underinsured, the math ensures their unique circumstances are weighted appropriately, not ignored. And here's the kicker. This approach isn't just theoretical. It's adaptable. Whether you're modeling climate risks or designing AI for hiring, the same principles apply. By mathematically locking in fairness constraints, researchers are building systems that are resilient to bias, without sacrificing accuracy. So next time you interact with an algorithm, remember, behind the scenes, mathematicians are working to make sure it's not just smart, it's just. Because in a world driven by data, fairness isn't a luxury, it's a necessity. Thanks for watching and stay curious.